Hey everyone, it's time for physics. Today, the photoelectric effect. So let's remember why light is a wave before I tell you that it's not. Remember that in one of our earlier videos, we shined a light through an opening between two books, and we found that the light coming in was able to bend around the corners, just like a wave can. And yesterday in class we saw a diffraction pattern caused by a light wave hitting a strand of hair. This is a cross section of the hair, and bending around the hair, causing an interference pattern on the wall, where the bright spots were areas of constructive interference and dark spots were areas of destructive interference. Light must be a wave, but it's also a particle. And here's why. So Newton's original idea of light being a particle was long forgotten until Einstein came along and explained this phenomenon called the photoelectric effect. And it goes like this. If we shine a light on a piece of metal, sometimes if the light is just right, an electron can be ejected from the atoms of the metal. So what we're going to do is we're going to look at the type of light that would eject an electron and the type of light that will not eject an electron, and see if we can figure out anything else about the nature of light. So we're going to try 4 different types of light. 2 blue lights, 1 dim and 1 bright, and 2 red lights, 1 dim and 1 bright. So I'm going to draw my metal plates here. So first we're going to start by shining a bright blue light on our metal plate here. And how I'm going to represent that is a blue line, many blue lines here. A very intense blue light. And we find that when we shine a very intense blue light, we are able to eject one of those electrons off. So a bright blue light, yes, it ejects an electron. Now let's lower the intensity of this blue light and see what happens. We find that when we lower the intensity, but the light is still blue, we are still able to eject an electron off. So a bright blue light, yes, it ejects an electron. A dim blue light, yes, that also ejects an electron. So now let's look at the red light. So I'm going to start with a really dim red light just to see what happens. And we find that even with a dim red light, there is no electron ejected. Okay, well, the natural thing to do will be to increase the intensity until we find an electron getting ejected off. And we're going to keep increasing the intensity. And we're going to keep increasing the intensity. And we find that no matter how much we increase the intensity of the red light, it still is not going to eject an electron. So if light is a wave, we should be able to knock off electrons just by increasing the intensity or the energy of the light wave. But it seems that what matters more so is the color or the wavelength of the light. Here, the red light wasn't able to eject an electron no matter how bright we shine the light. But the blue light, no matter how dim, we were still able to eject an electron. So this experiment verified that light can also behave as a particle. So to help understand this, imagine that we have a pool table and it's full of pool balls. So here's our pool table and it's full of pool balls. And of course the pool balls represent our electrons here. So if we shine a dim red light, it's like throwing a single ping pong ball at the pool balls and expecting the pool ball to be ejected off. Of course, we know that that doesn't happen. Okay, but let's say we throw 1,000 ping pong balls at the pool balls. Still, nothing is going to happen. But now let's say we shoot a bullet at the pool table. Well, you don't really need more than one bullet to knock off one of those pool balls. You would just need one.
Or just one.
So from this, we can also learn one other thing as well. That blue light is going to be more energetic than red light. And if we extend the electromagnetic spectrum to its extremities here, we'll get radio waves and gamma rays down here. So as we decrease the wavelength, the energy begins to increase. That's good for us because our cell phones run on radio waves, which are relatively harmful to living tissue, whereas as we move down, things like UV light and gamma rays are extremely harmful to living tissue. Einstein won the Nobel Prize for showing that light can behave not only as waves but particles as well. This is called the wave-particle duality, and it applies to every subatomic particle, just like electrons, protons, and neutrons as well. We're going to look at the wave-particle duality of nature more in our modern physics unit.
Or just one.